Hi, and welcome to this second video in this series on sequences. And in this video we're going to be looking at something called geometric sequences. And this video is going to follow very much the structure of the previous one on arithmetic series. We've got to go through the same process to work out our general formulas for how to find the sum and how to find the any particular term in the series, and then look at how we can use that in a problem-solving context. So here we go. Geometric sequences. What we've got with the geometric sequence is, rather than going up by the same amount each time, essentially what we've got is a common ratio between each term, which means it's being multiplied by the same amount each time. So that means you're from one term to the next, you're multiplying by a fixed value. So for example, if we have a look at that one there, and hopefully you can straight away spot what that fixed value is. Sometimes it's not so obvious, and then the easiest way to work out the common ratio is just to look at the two consecutive terms. So for example, if I take 54 and 18, if I do 54 divided by 18, I'm going to get my common ratio. And that would be the same as if I took any two terms, for example, 18 and 6. It's going to give me a common ratio, and clearly that common ratio in this case is 3. This one's slightly less obvious. I'll give you a moment just to have a little look and see what's going on, because what we've got here is alternating positive and negative terms. So we've got positive term followed by a negative, followed by a positive, followed by a negative. And hopefully by now you've realised that our common ratio here is minus 1/2. If I go from 1 times by minus 1/2, I get there, times by minus 1/2, brings back to a positive, times by minus 1/2, takes back to a negative, and so on and so forth. So you sometimes see these geometric series that have flipping positive and negative signs. And when that happens, it's because we've got a common ratio that's a negative value. So let's now have a look at how we define our generic formulae, which will tell us the particular term in the sequence and also the sum of a geometric sequence. And what we've got is, again, a geometric is defined by two things. It's defined by A, the initial value, and this time, instead of being a common difference, it's a common ratio that's R. So very similar structure to our arithmetic sequences. There's all our terms from A1 up to AN, and here we go. So there's our first term. Second term is A times by the common ratio. Third term is the second term times by the common ratio, or A times by R again. There we go. And again, we notice that the number of times I'm multiplying by the common ratio, here I've got squared, is one less than the actual term itself. Here I've got cubed. That one is the fourth term. So what that gives us, hopefully you can recognise that we've got A times R to the power n minus 1. And that is our formula for finding any particular term in a sequence. All right. Hopefully that's fairly simple. Let's move on and have a look at the summation one. And if you remember from the summation one from arithmetic sequences, we pulled a bit of a sneaky trick, the one that kind of the German guy Gauss pulled back when he was in primary school. What we're going to do is something similar, but rather than doing it by adding, we're going to do a little bit of shifting around. So what I'm going to do is actually multiply the entire series by the common ratio. So on the left-hand side, we've got R lots of the sum of the series. And on the right-hand side, each term is going to be multiplied by R. And so what I've got, my first term, A times R, is here, and I've deliberately written it. I've just kind of shifted it along, and you can probably see the reason for why I've shifted it along is so I'm lining up terms that are the same. And what that means is I've got my last term, which is this one here, AR to the n minus 1, times that by R, and I get this thing, AR to the n. What that now allows me to do is I can do a bit of subtracting. So on the left-hand side, we're doing Sn minus R lots of Sn, so we get that expression there. On the right-hand side, I'm going to subtract columns. So you can see I've got A there, and now these columns here, that's clearly going to cancel all the way through until I'm left with this term under here. So essentially I've got 0, take away that thing, so that's minus AR to the n. And so that's where we end up. All I've got to do now is a bit of factorising on the left and also a bit of factorising on the right. Let's do that now. And then to get that saying Sn equals, which is the sum of the first n terms of a geometric sequence, that's going to equal A over 1 minus R to the n all over 1 minus R. Now, this formula, we've got it in two versions. We've got that way round, but if I times top and bottom by minus 1, what I'm going to do is essentially flip the signs, and we've got that version as well. It works both ways round, and sometimes it's easier to use the top one, and you'll notice that it's easier to use the top one if I've got a value of r that's between 1 and -1, because then that keeps this thing here positive. But if r is bigger than 1, then I'm going to use this version, because again that keeps it all positive, and so yeah, I'm going to worry about minus signs. You'll see a couple of examples of that over the course of the next few slides. So here we go. First four terms of a sequence, 2, 4, 18, 54. That's our sequence that we talked about on the previous slide. So we've got a equals 2, r equals 3, n equals 10. First 10 terms. So a10 equals a, which is 2, times by 3 to the power of, and it turns out 10 minus 1, which is 9. And so our 10th term is 39,366. And as I can hope you appreciate, these sequences, the numbers get very large very, very quickly if you've got values of r that are above 1. And the sum of the first 10 terms, again, is just put things into the formula, and this time I'm using this bottom one here because that keeps everything positive. And so we get that. Plug it into the calculator, sum of the first 10 terms, 59,048. Okay, there again is our simple just plugging numbers into a formula. Let's have a look at the kind of question where we've got to extract some information of the question and do some calculation to find out a and r. Same kind of thing as we had with our arithmetic sequences, so let's take our information. So that's our first one. So we've got 27 over 4 equals ar squared. And let's take that piece of information, there's a5. So we've got 243 over 64 equals ar to the power 4. Again, what I've got is a simultaneous equation. Now, previously with simultaneous equations, we dealt with things by subtracting. Here I'm going to do it slightly differently. This may or may not have popped up in other contexts. But what I'm going to do here, rather than adding or subtracting, as you might be familiar with when you're eliminating a variable, this time I'm going to do some dividing. And you'll see the reason for that when we do some dividing on the right-hand side. So divide the left-hand side. I've got 243 over 64 divided by 27 over 4. That gives me 9 over 16. And on this side, ar to the 4 divided by ar squared. Well, if we do that division, hopefully you're happy that the a's will cancel. A little bit of index law gives us that being r squared. And so I've cancelled out the a. I've got r squared is 9 over 16. And now it's a simple enough job to come up with r is 3/4. Okay, so if r is 3/4, so we've got 27 over 4 equals ar squared. Plug in our value for r and solve for a, and we've got a equals 12. So therefore the sum of the first 10 terms from this sequence are going to be, again, bang the values for a and r into that formula. Notice this time I'm using the version where it's 1 minus r, because again that keeps this bit on the bottom, keeps this thing here positive, and we end up with 245.3 and a whole load of decimals. I've done some rounding there. Okay, like I said, similar kind of structure to what we had with our arithmetic sequences. Let's now move on and look at a contextual exam style question. So this one is to do with the insurance premiums on a Land Rover. So we've got car insurance reduces the annual premium by 7% each year, as long as we don't have a claim, up to a maximum of 10 years. And then after the 10 years, the premium stays fixed. So it is a geometric sequence, but we've got a little bit of fiddling around to do when we get towards the end of this, because we've got that period where it's fixed and the value doesn't change. So let's just have a look at what's going to happen. So in year 1, we've got our initial premium. That premium is going to reduce by 7% each year. So we've got our common ratio. So if I'm reducing by 7%, that's the same as multiplying by 0.93. So we get A10 equals 247.50. Our common ratio 0.93 and to the power 9. And so in our 10th year, we've worked out straight away that we're going to be paying a premium of £128.80. And then the following year, that premium remains fixed at that level. So for year 11, we've got that. Same in year 12, same in year 13, all the way up to year 15. So we've got those premiums for that part of our series. So how much does he pay in total for this Land Rover? So we need the sum of the first 10 years, which will be S10. And then on top of that, I've got what we're paying from years 11 to 15. So that'll be 5 lots of the £128.80. I know in total we've got the kind of 6 lots of £128.80, but I'm including this one within our S10. So S10, let's plug in the values. Let's just stick it into our formula. There we go. So we've got that 0.93 as our common ratio, £247.50. And then I've got 5 lots of the 128, so that's that £644 there. Bang all that into a calculator, so the total Bert is paying for his insurance over the 15 years is £248.68 and 49 pence. And there we go. Again, you'll find in a lot of cases in exam style questions, they will do things where it will appear to be either arithmetic or geometric to begin with, but then something changes and you've just got to think your way around it a little bit. No two questions are likely to be exactly the same. You've got to be able to apply your skills to whatever you're presented with. Okay, cool.